Okay, and this is number 18, that T sub k be a transformation of the coordinate plane that first rotates the plane k degrees counterclockwise around the origin and then reflects the plane across the y-axis. What is the least positive integer n such that performing the sequence of transformations t1 through tn returns the point 1, 0 back to itself? Okay, so let's just see what's happening here. We have the point 1, 0. Okay, so let's write it, let's do it like a polygraph where this is, we have an argument here with the angle. So it starts at angle 0. After the first one, so we're gonna rotate it 1 degree counterclockwise and then reflect it across the y-axis. So that would go over here, and that's going to be 179 degrees. So after t1, the point goes to 179. Okay, now let's see t2. We rotated 2 degrees counterclockwise, so that's going to be 1 degree going that way, and then reflected across the y-axis, so that's going to be -1. And then t3, we'll have it here, and then it'll go 2 degrees, and then we reflect it across the y-axis, that's going to be 178. t4, we have to, so that'll be -2. So like 178 plus 4 degrees, that's 182, and then reflected across the y-axis, that's -2 degrees. Okay, so it seems like the pattern is just between every 2 consecutive odd ones, it just decreases 1 degree, and then between every 2 consecutive even ones, it also just kind of goes down 1 degree as well. So I think, yeah, okay. So let me just think. So if we look at these negative ones, it's going to have to go 360, like it's going to have to decrease by 360 degrees to get back to 0. So like for example, we'll have -1, -2, -3, and to get back to 0, point 1, 0, we have to go -360. But if we look at the positive ones, 179, 178, that's only going to have to decrease 180 degrees. So we should look at the odd ones to see when the point 1, 0 gets back to itself. So T1 is 179, T3 is 178, T5 is going to be 177, and let's see, if we let's just do it like this. Let's write another sequence like Q1 equals 179, Q2 is 178, Q3 is 177, and Q180. Or, no, wait. Yeah, okay, so it'll be 0. Okay, Q180 is 0, and notice that to get from the series T, or the sequence T to Q, actually no, sorry, to get from Q to T, we multiply this subscript by 2 and then -1. So for example, Q3 to go to T5, or corresponds to T5, we multiplied 3 by 2 minus and then minus 1, that's what, 5. Similarly, 2 times 2 minus 1 is 3. Okay, so the first time it's going to get back to itself is q sub 180. So we multiply 180 by 2 and minus 1, that's going to be T359. And that'll get the point back to itself. Okay, so the answer is going to be 359. Okay, so this will be the second to last one. This is the 2022 AMC 10A number 19. Define L sub n as the least common multiple of all the integers from 1 to n inclusive. There is a unique h such that the fractions 1 over 1 plus 1 over 2 all the way to 1 over 17 is equal to h over L sub 17. What is the remainder when h is divided by 17? Okay, so this is essentially, okay, so what we're essentially doing in this problem, it's basically just putting all these fractions under a common denominator, which is L sub 17, and then it wants us to find the numerator mod 17. So first let's find L sub 17. This is going to be the least common multiple of 1, 2, 3, all the way to 17. So the greatest power of 2 we're going to have is 2 to the 4th, which is 16. The greatest power of 3 is going to be 3 squared, which is 9. 5, we're only going to have 5 to the 1st, so times 7, times 11, times 13, times 17. So actually what we can do is just multiply both sides by L sub 17. So we're going to have L sub 17 over 1 plus L sub 17 over 2 all the way to L 17 over 17 equals h. And we want to find h mod 17. So actually we don't have to compute any of these because L sub 17 has a factor of 17 here. So when we divide by any of the numbers from 1 through 16, it's still going to be divisible by 17. So the only one we actually have to consider is this one here. So L sub 17 over 17 is just going to be this. Get rid of that one. And we just want to find this product. I'll write it over here. Times 13 mods 17. Okay, this is 16, which is -1, times 9, times 5, times 7, and then we can probably just also write these as -6 times -4. And there probably isn't a good way to do this from here. Well, we can get rid of this -1, make this +6. 45, 5 times 9 is 45, which is 11 mod 17, 77. This is 68, so this is 9, 77 turns into 9. 6 times 9 is 54, which is 3. And then times -4 is -12. So that will just be 17 minus 12, which is 5. And that should be C. Okay, and finally, the last problem, number 20. A 4-term sequence is formed by adding each term of a 4-term arithmetic sequence of positive integers to the corresponding term of a 4-term geometric sequence of positive integers. The first three terms of the resulting four-term sequence are 57, 60, and 91. What is the fourth term of the sequence? Okay, so let's just write each of the sequence in terms of variables, because I'm not really sure how to start. We have a plus d, a plus 2d, and a plus 3d. This will be our arithmetic sequence. And then similar, we can just do b times r, br squared, and br cubed as the geometric one. And then we're given that a plus b equals 57, a plus d plus br equals 60, and a plus 2d plus br squared equals 91. Okay, so we have 4 variables, but we only have 3 equations. So that kind of implies that we're going to have to use the fact that they're positive integers to find the possible solutions, since it's not possible to solve for 4 variables in 3 equations. So let's just try to do some manipulation. Let's subtract, I guess, these two, the second and third equations. We get, the a's cancel out, we get d plus br squared plus br equals 31. I'll factor out the br, I guess, so br times r plus 1 equals 31. Oh, actually, sorry, this will be minus br, and this turns into negative 1. Okay. And we can do the same thing for equations 1 and 2. So subtract them, the a's cancel out, we get d plus br minus b equals 3. This will be d plus b times r minus 1. Okay, and then, yeah, we can combine these two equations. So if we subtract this one and this one, the d's will cancel out, and we'll get br minus b times r minus 1 equals 28, because both of them have an r minus 1 term. Oh, actually, we can also factor out b from this. Okay, so this is the same as b times r minus 1. So we get b times r minus 1 squared is equal to 28. And let's see. Well, I guess from here we can... Okay, so we know that r minus 1 squared has to be an integer because b is an integer, since it's the first term of the sequence, the geometric sequence, and the problem says that it's a sequence of positive integers. So r minus 1 squared is an integer, which means it must be a factor of 28. So we actually have two cases. Either r minus 1 squared is equal to 1, or r minus 1 squared is equal to 4. Because, well, we know that they're both integers, which means they must be both factors of 28. And the only perfect square factors of 28 are 1 and 4. In this case, we're going to have r equals 2, and this one will have r equals 3. So I guess the only way to just check which one works is by just testing both. So let's say r equals 3. Then b equals 7, because in this equation we'll have 3 minus 2 squared, which is 4, so 4b equals 28, b equals 7. Then plug it into here, we get a equals 50. And then finally, I guess we can plug it into this equation, number 2. 50 plus d plus br is 21. So 71 plus d is 60, d is negative 11. Okay, now let's see if this works. So we're going to have to sequence 50, 39, 28, 17. The bottom one will be 7, 21, 63, 189. And yeah, it seems like this works because the first term of our new sequence is 57, which is 50 plus 7, 39 plus 21 is 60, and 28 plus 63 is 91. Okay, so yeah, this is satisfied. So our fourth term is just going to be 17 plus 189, which is 206. Yeah, so that's E. So that's all 6 problems. I hope you all enjoyed. I'll probably be posting a similar video on the 10B or the 12B. But of course, if you have any specific problems you would like to see, just leave a comment. Yeah, that's it.